All right, it's my great pleasure to introduce our next speaker. Quite unusual speaker, perhaps, for a science conference, or maybe not. It's Michael Strevens, who is a writer and professor and writes about science, understanding, complexity, and the nature of thought, and teaches philosophy at New York University. His most recent book, which I ate up, and I highly recommend, is The Knowledge Machine, and sets out to explain how science works so well and why it took such a long time to get there. So we'll have Michael give a 50-minute presentation, and then we'll have, again, a conversation about philosophy, about how philosophy applies to perhaps our really more practical work, and what's up for the next century. Michael.
Well, thanks very much, Jeff, and it's great to be here, my very first geology conference, as a matter of fact. Thank you. So I thought I would talk about just one aspect of my work on the nature of science and how it works that's connected in particular to subjectivity and objectivity in science. And I think that aspect is both, it's first of all very relevant to what I'm doing actually at Cobalt, where I'm working with on the epistemology of exploration, and also really relevant to the very biggest questions about how society can take advantage of science, can best take advantage of science to stave off disaster and to make the world in general a better place. So if in a single slide, my ambition in my thinking about how science works is to understand why Aristotle, pictured there on the left, who was a supremely talented thinker, an extremely systematic thinker, a wonderful observer of nature, somehow failed to create the kind of lasting science, although he wrote books on physics, biology, which are intellectually dazzling, incredibly well-informed both empirically and philosophically, failed to create the kind of lasting foundation that a thinker like Einstein or the many other thinkers who created modern science were able to create, a kind of platform that survived after they left and on which further achievements could be built. What I'll do today is at Jeff's suggestion, is just talk about a single example and take my lessons from this single example. It's an example that involves, in fact, Einstein himself. Now he's on the left side. And he's talking there to Arthur Eddington, the great English physicist, who is famous, perhaps above all, for his test of Einstein's theory. Shortly after the final version was published in 1916, his one of the first real tests of the theory that measured the angle by which, or the degree to which, a gravitational field would bend a light ray. Einstein's new theory made a prediction that was quite different from the Newtonian, the classical physics that existed before Einstein. As with many great scientific experiments, the basic idea here was conceptually very simple. We just go out and watch a light ray pass by a very massive object and see how much it's bent. And if it's what Einstein says, then 3 cheers for Einstein, and if not, then maybe back to the drawing board. You do need a very massive object. The only really suitable object at the time when Eddington went off to do this measurement, the only object that was really big enough was, in fact, the sun. So the plan was to look at the light from stars on the other side of the sun, the stars that were behind the sun at a given point, and see to what extent they appeared to be displaced in the way that things look like they move when the light coming from them is bent. Again, very simple. You could illustrate it with a picture, explain it with a pencil and paper. I won't do that, just to save time. But the difficult thing about this is that the sun, as well as being very huge, is also very bright. And really, this measurement could only be carried out if its light was obscured. In short, what was needed was a total solar eclipse. Fortunately, one was coming right up. It was one where the zone of totality would pass over, as you can see, part of South America and part of Africa. And Eddington, to test Einstein's theory, created an expedition that actually sailed to two different places on the path of the eclipse. One you can see in northeastern Brazil, Sobral, and one on Principe, the island off the west coast of Africa. Here's the setup in Sobral. As you can see, there's two telescopes here. In front of the telescopes are two mirrors. So the telescopes are laid out flat. It was too much to actually bring all the mountings and so on. And the mirrors are directing the light from the sun, more exactly from the stars around the sun, down the barrels of the telescopes to cameras at the end. You would create photographic plates that looked like this. This is a negative. So that's the sun eclipse. This is one of the plates from the experiment itself. The sun eclipse, and maybe you can see at the top right-hand corner, there's a couple of faint lines, and those are picking out the positions of the stars. And really, all that's being done here is these photos are being taken of those stars during the eclipse, and then again without the eclipse, in the middle of the night, without the sun, that is. And the positions are being compared, and we're just looking at how much the little dots on the photographic plates appear to have moved. That amount is not very large. It's actually it's about a 60th of a millimeter that Eddington was looking for. So not a straightforward experiment to carry out in that respect. It's actually that's about a quarter of the size of the dot on the photographic plate that is the star. But still, measurements like that had been performed. They knew how to do it. Of course, things don't always work out the way you intend them to work out. Eddington himself was on Principe, and as sometimes happens during a solar eclipse, the weather was very cloudy. So he managed to get a couple of photos showing a few stars. He did a lot of calculation to extract a result that looked promising for Einstein, but this clearly was not very much information. In Brazil, however, the skies were clear, and one of those telescopes of the two I showed you in Brazil came back with some really nice data that gave results actually that were not only too big for Newton, but even a little bit too big for Einstein. But not so much bigger that it didn't look like a pretty successful result for the Einsteinian idea. Unfortunately, the other telescope was not so cooperative. It came back with results that looked more like what the old Newtonian physics predicted. However, and this is, I'm stopped for a moment just to remark, this is very typical, of course, of scientific research. A simple experiment that's actually really hard to carry out, subject to many, many factors that can make things go wrong, especially given the very, very small changes you're looking for, the very small quantities you're measuring. And on the day, all sorts of things go wrong. There are clouds in one place. In another place, this telescope, as you can see from the slide, these results may be Newtonian, but also there was a blurring in the plates. So clearly the apparatus wasn't all working exactly correctly. Something was a bit off, but what? Here is the discussion. This is the original paper where Eddington and the team presented their results. Here's the discussion of those results, where they first of all point out that there was something wrong with those plates. The question is, though, that now they're not so blurry that you can't get information out of them, and in fact get from them an estimate of the bending power of gravity on light. And in fact, that estimate looks like it proves Einstein wrong. But why the blurring? Now, it could be that the blurring is just a matter of the whole setup being a little bit out of focus, in which case that would be good information, not perfect information, but good information. But it could also be that something had gone more systematically wrong, and in fact there was a systematic distortion of the star field, in which case the results that they're getting from the plates would be quite misleading. Okay, but which was it? Well, you can see here in their own words, they're thinking about this. They simply say, it's difficult to say which of those two it was. Could have been a little bit out of focus, really bad for Einstein. It could be a systematic change, in which case the results basically should be ignored, in which case all that's left is results that are good for Einstein. A complicated situation, again, very typical in scientific experimentation. What did Eddington and the team say at the end? Well, they decided simply to, in effect, ignore. I mean, they reported very meticulously on the results of that telescope, but then essentially put aside the results and concluded that there is very little doubt that Einstein's that the effect of gravity on the light is as Einstein's theory says, and as classical physics, Newtonian physics, does not say. So it looks like a great victory for Einstein. But as some well-informed observers at the time commented, that seems a little hasty. By the very lights of the experimenters themselves, who say they can't really give you a reason to think that there was a systematic distortion rather than simply a loss of focus. So this is the American astronomer W. Campbell, and he says, politely, the logic is not entirely clear here. Okay, so what should we think? This is a case where let me go back one slide. The question of what Eddington's team should have done is a question that is still being debated today. Okay, I say something about it in my book. We had a lively little discussion about it when I gave a talk at the talk to Kobold about my book, about whether Eddington was really fudging or whether he made the right call. I mean, in some sense, we know he made the right call, but whether he made the right call in that specific situation. Physicist Daniel Kennefick, in this book from 2021, is still defending Eddington against his detractors, who say he was too hasty to interpret the experiment as a decisive victory for Einstein. However, that's not to say that people are still arguing about Einstein, or certainly they're not still arguing about whether Einstein makes the right prediction about the bending angle of light. There's pretty much no question that Einstein's theory of relativity does in fact make the right prediction. And you can, now let me tell you that W. Campbell is not just another consumer of this literature. He is was one of the major experimenters who did exactly what Eddington's team was doing, taking photographs of eclipses. He was interested in spectroscopy above all. But when Einstein's ideas hit science, he also realized, as Eddington did, that the theory could be tested by taking these kinds of photographs. And he himself visited a number of eclipses, actually beginning before the final version of Einstein's theory was formulated in 1914, to Russia. As you probably know, 1914 in Russia was not the right place to be. That experiment was a disaster because World War I began in the middle of that measurement. Again, in Washington State in 1918, things went wrong there. But then, in 1922, again, Lack went to Australia where there was another eclipse, and here produced results, the kinds of results that actually pretty much allayed everyone's doubts, including his own doubts about whether Einstein's theory made the right prediction. Okay, that's my little story. And what I want to illustrate with that story is the way that the subjective and the objective work together in science. And there's a lot to say about this, but I'll just extract one moral. First of all, what is often extremely subjective is the interpretation of evidence. The results of that telescope in Brazil, should we dismiss them, or should we take them as giving us some reason at least for pause in accepting this radical new theory of gravity that Einstein had suggested? There was simply disagreement about this. You know, I think Eddington and his team were pretty sincere in thinking that they had good evidence. Lack was pretty sincere in thinking that a question mark hung over that evidence. There was a straightforward disagreement about how good the evidence was, and this is very much the case throughout science. Many scientists are here, of course. I hear over and over again when I talk to scientists, yes, well, they think they've gotten it right, but there's a problem with that method that you need to know about. That's the subjective side of science in the interpretation of specific experiments, specific sets of evidence. But as we also see in the story of the eclipse measurements, there's an objective side. In the end, pretty much everyone agrees, and agrees rightly, that Einstein's theory is making the right prediction for the bending angle of light. And this is more of a long-term process. So I would emphasize, if I had to sum up in a single pithy sentence, subjectivity in the short term, when it comes to figuring out what's going on, objectivity in the long term. Of course, there should be a long footnote to that, but I won't add it right now. Instead, I want to just talk for a couple of minutes about the way that science manages the situation. On the one sense, the short-term subjectivity. On the other hand, or manages the short-term subjectivity in a way to realize the long-term objectivity. I think the single most important element of science in making this happen is something that I call the iron rule, science's iron rule. This is a rule this is, in some sense, this is what philosophers and many other thinkers have been looking for when they're looking for the nature of the scientific method. But it's not actually a method. In some sense, it's not methodological at all. Instead, it's more like, as I sometimes like to call it, a speech code that applies to the way that scientific research is presented in the official channels of scientific communication, primarily science journals. Okay? So all this rule is doing is restricting how you can express yourself in a journal. It has nothing to say about how you decide to go out and perform what experiments and how to think about those experiments themselves. It's simply a constraint on reporting. And we can actually see that constraint, I think, in action in that little segment of the eclipse paper I showed you. So what does it say? Here are the two most important things, and the two things that are most relevant right now to what I'm saying right now. First of all, scientific argument should be entirely restricted to empirical testing. Someone like Eddington, who is in fact, more of a mathematical physicist than an experimenter, and who was drawn to Newton's theory by the elegance of, I think in particular, its explanation of the correspondence of inertial mass and gravitational mass. Doesn't matter if you don't know exactly what I mean there, but drawn to the elegance of the theory, nevertheless had to go out and orchestrate this entire expedition, which took a good 6 months just in the traveling, let alone the organization and the mopping up and so on, in order to argue officially, as the science journals require, for the theory. So the iron rule, well, it tells you what empirical testing is, and then it says that's the only thing that gets into the journals. And the other side of this, and now really getting towards the question of subjectivity, in those reports, everything subjective must be omitted. Now, my colleague at NYU, the historian of science, Matt Stanley, who's one of the leading experts, maybe in fact the leading expert on the history of the eclipse measurement. He thinks that, in fact, the experimenters in Brazil had some reasons to think that the distortion in those of the mirror, the telescope mirror, and therefore of the experimental results was, in fact, a systematic distortion and not just a lack of focus. But it was the kind of reason that you might call a hunch. You know, a very well-educated hunch. These are people who were experts in carrying out these kinds of experiments. But it wasn't the kind of thing that could be presented in the kind of cool, objective prose that's required in a scientific journal. So they simply couldn't express their reasons. And in some sense, maybe not even communicate their reasons for going the way they did on that evidence. So the iron rule says, leave all of that out, just the facts, as it were, just the objective facts. Where subjective basically means anything that there might be disagreement about, and objective means the rest, which would include simply reports on the measurements, the positions of the little dots of lights on those plates, performing statistical tests, that is, cranking through the appropriate mathematics and so on, reporting a p-value or whatever, and also truths that are generally accepted by the community. That stuff all goes into a paper, nothing else. So this actually requires a kind of a purging of scientific communication when it's put on paper in a journal article, as opposed to, say, in a popular book or something like that. A lot that is important and relevant is being left out. a lot that is subjective is being left out. Some of my colleagues in philosophy think too much is being left out. You know, there are important reasons that bear on what to think about the evidence are being left out. But I think there's a certain strategic genius to these restrictions, even if they are, as I say in the subtitle of my book, strictly speaking, irrational. It sets up science as a kind of a game. Now, when I call it a game, I don't mean it's not serious and important and that the players don't really care about getting to the truth. But there's a certain artificiality that's imposed by the iron rule. Because to get ahead, you know, to receive any kind of credit for your research in science, you must publish it. It's got to be published in the journals, and therefore it's got to be published in a format that is allowed by the iron rule. If you're going to be a scientist, you have to play the game. The iron rule lays down the legitimate moves in the game, the sorts of things that could appear in for example, in the report of the eclipse experiment. That means sidelining all of these disagreements about the interpretation of the evidence, okay? Just simply leaving them out, even if what's left over is sort of creates, well, as Campbell said, a rather obscure logic. But it works, because in the end, what really matters is not attaining agreement on the results of any particular experiment. As I said, people still do not agree. People who have spent years and years of their lives thinking about it still do not agree on whether Eddington and their team did the right thing in putting aside the Sobral experiments, whether that was a reasonable thing to do at the time. But it just does not matter. What matters is that in the meantime, people like Campbell himself have gone out and done more experiments. What is really driving science towards its, objectively towards its consensus is this kind of duplication and reduplication, well, with many, many variants, of the kind of experiments until there is no longer controversy, not because people can all agree on what we should think about the results of the Brazil measurements, but because those measurements don't matter anymore, because there are so many other besides. And it's this science game, as orchestrated by the iron rule, that clears the way, in effect, for this process by, first of all, making it not only unnecessary but impossible to argue in the official literature about the interpretation of evidence, simply inviting the production of more evidence that piles up until eventually, with any luck, we get to the truth. All right, thank you very much. Shall I join you over a little bit?
Yeah, great. That's amazing, Michael. I read your book with great enthusiasm. And in the beginning of your book, when I started reading it, I was looking, I've read a number of books on this. Karl Popper and Kuhn were two philosophers that you really put out there right from the beginning. So you didn't mention other philosophers like too much as like Bertrand Russell or David Hume or Thomas Bayes, who wasn't a philosopher, but the Bayesianism that came from. So can you talk a little bit more what it was your fascination with Karl Popper, and also maybe then perhaps in the context of what we're doing here?
Sure, yeah.
You have to click something.
Philosophers. Okay. So I think the eclipse experiment Popper's idea was that science is all about falsification. We find an experimental result that's inconsistent with a theory, we throw away the theory. But the eclipse experiment illustrates nicely why no unsophisticated version of that could possibly ever be successful. I mean, in the light of those conflicting results from the two telescopes, you should throw away all the theories. To put it another way, the only way a theory could be retained is if it makes inconsistent predictions. Always, when thinking about what to do about a theory, you're thinking, well, what might have gone wrong with the experiment? Were the conditions really what we thought they were, et cetera, et cetera? So in the short term, I'm going to go back to my short term and my long term. In the short term, something like Popper's conception of falsification is not very useful to scientists. However, in the long term, when we're looking at the case where the evidence is piled up to a point where there are no longer any deep worries about the experiment systematically going wrong. Of course, this can take a very long time. You know, when the particle physicists demand a kind of a 5 sigma standard for a discovery, what they're doing is committing to a very long, arduous process. But eventually, we reach a point where something that at least has the character of falsification really can occur. Everyone can agree, yes, Newton's theory is just not making the right prediction about the bending angle. So that's what I see as the Popperian aspect to the way science really works.
Great. I want to follow up on the short term and long term, and maybe within our own academic enterprise. One of the challenges we have today is things like climate change and energy transition. And so doing science in the long term is almost, well, we can't solve these problems. We have to solve them in the short term. We can't just wait for long-term science to advance. What does that mean for science itself, right? And also the philosophy of science, now that we have suddenly, which in the past they didn't have, these really urgent necessities that are demanded from science and engineering?
That is such a good question, and really, in some ways, the kind of the great question I think that we're all facing right now with respect to the kinds of emergencies where we would like science to save us. And I think there's no happy answer in the sense that, well, maybe I shouldn't say that. There's no simple happy answer. It really is the case that we need answers sooner rather than later, and it really is the case that the way science works is not designed to give us definitive answers in the short term. Of course, there's nothing else that's going to give us definitive answers in the short term either. Science is still the best thing we have, but what we're going to have to do is find a way to deal with the fact that what we kind of think of as the paragon of scientific achievement, discovery. Science has found out that. Scientists have discovered that. That is no longer a useful way to think about what science can provide for us. We need to somehow become comfortable with a science that hasn't made its mind up, but is still overflowing with important information. Find a way to use that information. So in the case of climate change, we have at great effort created the UN's IPCC that spends a bunch of scientists who spend years and years of their time trying to distill what can reasonably be drawn from the very complex state of you could call it knowledge about climate change, but what it really is simply well-educated uncertainty. Yeah. That's not an easy solution, but it's certainly better than nothing.
Yeah, absolutely not. So before we open it up to a couple of audience questions, I hear you got a promotion, which is chief philosopher at Cobalt Metals. I've never heard about a company that hires a chief philosopher. So can you tell a little bit about that and your role with Cobalt Metals? Are you going to discover big copper deposits?
As I think many people here know, Cobalt is an epistemology company that funds itself by making mineral discoveries. Or at least that's how Kurt put it to me yesterday. So the real question is why there aren't more philosophers working on Cobalt's epistemological processes. In fact, I think the founders of Cobalt, Kurt, Josh, the data scientists who work there are, in some sense, already themselves the epistemologists I'm talking about. My role there is to kind of pitch in and some lead the way, if you like, or maybe just to organize the management of uncertainty in various ways. That's already going on at Cobalt.
Yeah.
I'm helping out as best I can, but I discovered a company that was already doing epistemology, and where in some sense I'm just another philosophical cog in the machine.
All right, I like that, the philosophical cog. All right, we have a couple minutes here for some questions from the audience. Anyone wants to chime in on perhaps their own companies and their philosophy, what their approaches are or not are, or how they'd like to see some of these ideas integrated? We have two people right there. Can you wait for the microphone?
Hi, thank you. No, thank you very much for the talk. And I see you talk about irrationality. I just wonder why would you put the idea of hunches, intuition, or the concepts of beauty, maybe things like that, as irrational, when maybe these are our ways of seeing harmony, order, symmetry, things like this? So maybe why would you separate that as being irrational from other things?
Great question. In fact, I'm 100% with you. Those things are not irrational at all. They're hard. It's hard to articulate their value, but they're extremely valuable. What I see as being irrational, although highly advantageous, is the way that the Iron Rule excludes them from what you might call official scientific argument. So here are things that many, perhaps every scientist thinks are valuable, and yet they find themselves unable to talk about in their writing. But I think actually this is an enormous relief. It takes away the burden of having these arguments about the evidence and allows scientists to get on with producing more observations and reaching that long-term objectivity.
Hi, I look forward to reading your book, but I haven't read it yet. My question is more about this industry, this sector at the moment, where we have models, and a number of geological models are based on 3 dimensions and tacit knowledge that can't really be tested. And then on the engineering side, there's tests and retests and a more 2-dimensional method. And then on the community side, we're out to maybe 4 dimensions of information, and it's quite variable. So how do we link those in this sector effectively?
Thanks. Yeah, I'm sure there are at least 2 kinds of problems that you've pointed to, I think. So as far as the first kind of problem, which is simply about discovering the structure of the underground, I think I'll just echo the Cobalt slogan. Our job is to make mineral exploration scientific. In other words, to, as far as possible, find ways to turn the hunches, the guesses, the surmises into a kind of a systematic exploration of different hypotheses about what's going on down there. That's the goal at any rate. Another problem, though, is to take what's left entirely tacit in the way that the kind of science I'm talking about is working, namely the information that's implicit in those hunches. Even if you think of it as being encoded just in particular, in what we might call prior probability distributions or maps of uncertainty. So I think science works by simply leaving that stuff up to the individual scientists. But in a company that is spending a lot of money to, as it were, produce that information, that might seem too irrational. And so a real challenge is to find a way to, if you like, codify as far as possible the naturally subjective side of these endeavors, which is both good within the company because it allows the company to take advantage within itself of that information in a systematic way and transparent way. and also for people outside the company insofar as it makes this knowledge available to every interested party. I think that is a work in progress, but it's one of the big ambitions I think that we have, and one of the things I really look forward to working on.
Okay, well, we'll have to keep it there. Michael, thanks very much, and we look forward to more of your work.
All right, thanks very much.